Hello, so in this video we'll talk about the isomorphism of graphs. So an informal definition of isomorphism is similarity. So we say that two graphs are isomorphic if we can, in general say that they are similar. So for example, if we draw a graph like this and then we draw a graph like this, so then it's easy to see that this graph is similar to this graph because there are three vertices and one is, they form an one is connected to the next one and the next one is connected to the third one. So similar is the pattern here. Okay, but then imagine we have a complicated graph and we have to see whether they are similar like that or not, so we need a proper definition. So let's go. The proper definition of a graph isomorphism goes like this. We say that graph G, which is equal to a set of vertices and set of edges, is said to be an isomorphic real graph G prime, which is defined by a set of vertices V prime and set of edges E prime if there exist one-to-one functions from G to G prime and E to E prime such that a vertex in V is adjacent on an edge in E if and only if GV is adjacent to HE. So for example, what we are trying to say is if we have a mapping from this V to this V dash and this E to this E dash, and if a set if a element of V is adjacent to an element of E in G, then the corresponding element which was mapped by V on V prime is adjacent to the corresponding element which is mapped from E to E prime. And that H should be 1 to 1. Okay, but this can be simplified for simple graphs. Remember, what is a simple graph? A simple graph is one which has no multiple edges between two vertices and there are no loops. So for simple graphs, we only want to define our function from vertices v to v prime. So for simple graphs, g and g prime are isomorphic if there's a one-to-one function from g to g prime such that if uv is an edge in g, where u and v are in this v set, then if and only if that function applied on u and that function applied on v makes an edge in g prime. Okay, so this is typically, we'll see an example here how this definition comes into play, but this in general typically is a hard problem to solve. But we can check some properties quickly if two graphs qualify to be isomorphic or not. Some of these properties are the degree sequence. The degree sequence of one graph should be equal to the degree sequence of the other graph. Similarly, if you see here, we have 1, 2, 1. Here 1, 2 and 1, or 2, 1, 1, because degree sequence is always non-increasing. Okay, and same here. So this is one check. Okay, and the number of vertices both sides should be same, otherwise the graph cannot be one to one, and number of edges should be same because otherwise graphs won't be one to one. Sorry, not the graph, the functions won't be one to one. And if any of these is different in two graphs, they are not isomorphic. But however, if these conditions are satisfied, then there's no guarantee that they are uh, isomorphic. Okay, now let's go to an example here. We have a graph here. This is my, for example, G, and this is my G prime. Okay, now if I have a mapping, now are they simple graphs? They are simple graphs, so I can just find a mapping from the set of vertices of G to the set of vertices from G dash. Okay, so I can say S is mapped to A, we can say T is mapped to B, we can say U is mapped to C, we can say V is mapped to D, we can say W is mapped to H, X is mapped to G, Y is mapped to F, and Z is mapped to E. Okay, so then this is my mapping here. Okay, but how does this mapping make them isomorphic? So let's see. Adjacent vertices of W are V, Z and X. So V, Z and X. Okay, so what is the image of W is H. What is the image of V is D. What is the image of Z is E. And what is the image of X is G. So H is connected to where? H is connected to D, G and E. So D, G and E. So then that means that when we make these mappings, all the edges are conserved based on the new translations or new mappings. And you can check it for each vertex here. You can check it for, and then you just see the connected vertices of any vertex in G, and then check the mapping of each of those vertices, and then go to G prime and see whether that connectivity is maintained in the new mapping. Okay, so this means that G and G prime are isomorphic. Okay. Okay, now let's come to another variant of this problem. Now we have to find all non-isomorphic graphs with some fixed condition. So then the condition I'm going to use is that we have 3 vertices and less than 2 edges. Okay, so first of all, let's start with 0 edges. So for 0 edges, I have just one graph. Now for one edge, I have this guy and I have this guy. Do I have any more? Because any graph with 3 vertices and one edge will be either of this form or it will be of this form. Now let's talk about 2 edges. Okay, so 2 edges can be like this. Now we are talking about undirected graphs here. So undirected. Okay, so this is one version. Then one is this one. Then one is this one. Okay, then we have one is this one, and then we have one is, and then we have one is this one. Okay, so now you can check that these are all the graphs which have 3 vertices and less than 2 edges are isomorphic to one of these versions, and none of them are isomorphic to each other. Okay, okay, so this is another way of, for example, if you know the number of vertices and if you know the maximum number of edges, so then you can find the possibilities of how many basic non-isomorphic graphs are present, and those graphs can be isomorphic to one of those. Okay, okay. Now we have a graph which is called a self-complementary graph. A self-complementary graph is a graph that is isomorphic with its complement. Okay, so just a recap about what a complement is. So a complement of a graph denoted by G bar is formed from the same set of vertices as G, but an edge is present in between 2 vertices in G bar if and only if it was not present in G. Okay, so let's start with the example of a self-complementary graph. A self-complementary graph is typically like this: A, B, C, and D. So this is my G. Now first of all, let's find the complement of this guy. So complement has the same vertices, and the edges present here are not present here. Edges absent here are present here. So this is there, this is there, and this is there. Okay, now let me just say this is my G prime, just to change the labeling here. Okay, now if I have the labeling here, B is to A prime, C is to D prime, A is to C prime, and D is to B prime. So now you can check that this mapping conserves the edges or the isomorphic definition to make them isomorphic. Okay. Now, interesting observation in this is that what we have to find, we have to find condition on V for G to be self complementary. Okay. So this is what cardinality of the set of vertices here. Okay. Now note that, so first observation is that G and G prime must have same number of edges. Okay. Now let's say we have this is equal to small v. Okay. Now what is the maximum number of edges for a graph with vertex v? So this is equal to, note that if we have 4, then we have 1, 2, 3, 4, 5, and 6. Okay, so then this means that for 4 we have 3 plus 2 plus 1 edges maximum. Why? Because first can be connected to 3, second can be connected to 2, and third can be connected to 1. So similarly, for a graph with v edges, we can say the first can be connected to v minus 1, the second can be connected to v minus 2, and the last will be connected to 1. So this is equal to the well-known formula, which is equal to v times v minus 1 over 2. Okay, so then this is equal to v times v minus 1 over 2. So this means that this is the maximum number of edges. So this means G must have half of this and G bar must have half of this. So this means edges in G and G bar must be V times V minus 1 over 4. Okay. So this means that the number of edges, then the other observation is that the number of edges are always integers here. So this means either V is a multiple of 4 or V minus 1 is a multiple of 4. So here we can say V is 0 mod 4, which means V is a multiple of 4, or we can say V minus 1 is a multiple of 4. So we can say V minus 1 is 0 mod 4, or we can say V is equal to 1 mod 4. So this is a condition on the graph that to make it self-complementary. Now note that there's another condition that the edges should be equal to this thing. So first of all, we check whether V is, when we divide by 4, the remainder is either 0 or 1. If that is the case, then we count the number of edges. If the number of edges is given by this expression, then we can say that it qualifies to be self-complementary. Okay. So this is a brief introduction about graph isomorphism and some corollaries which are based on the isomorphic definition, namely self-complementary graphs and finding all the non-isomorphic versions given a condition on the number of vertices and number of edges. So hope it was easy to understand, and thanks for watching. Hope you liked the video.